All right, good morning. Can you all hear me okay? Okay, all right. So, I gotta erase this. Sorry for the delay. I was emailing you guys, so it delayed me getting ready my equipment. So on Friday, when you walk in, I'm going to give you a short quiz on the lab video I just emailed to you. Okay, I emailed it twice to you folks, so you should have that lab video. So when you walk in, there'll be a brief quiz on the video that was emailed to you and the document related to the lab. I want you to come in prepared, okay? The equipment will actually be set up today, probably after this class by Tyler, and you can come in and play around with the equipment if you want to play with it. And if you feel comfortable enough, you can already get tested on the lab, on the oscilloscope, okay?
And
Any questions on that?
This quiz is different. Sorry, this quiz is different from the like us showing that we know how to use it, right?
Yeah, this is a written one because I want to make sure that you watch the video.
Okay.
Yeah, and based on based on evidence that I have, I mean, some people are not even watching these video lectures, and so I need folks to watch the video so they can come prepared on Friday, and maybe try to take the actual practical quiz. Okay. I also want the process to be efficient in terms of the open lab. So if people aren't watching the videos, it'll be a mess. I mean, the last lab that, I gave you guys a month and everybody was doing it the last minute. So I kind of need you guys to, I need to find a way to get you guys ready for Friday. So this is the way I'm going to do it. Okay. All right. Exam 4 is on the 19th, and we're pretty much on track. I might use some time on Friday's lab to cover some material, okay? But we'll be pretty much on track for that exam, okay? Is my voice real choppy today? Oh, let me check. Hold on a second. You guys can't hear me? Okay, I'm sorry about that. I'm sorry that it's harder to hear me. I'm not sure what the deal is. I have the same setup. Hold on a second. I think it was set to the wrong mic. I don't know what happened. You should be able to hear me better now, right?
Yeah, that's much better, I think.
Yeah, for some reason, Zoom was set up for the computer mic, which I'm like 8 feet away from it. And I have one on my, I have one here, so, okay. All right, so now we're okay. All right, sorry about that. All right, so you'll use, anyway, the DC Circuits Lab is due Friday. And then the scope quiz. Oh, and I forgot. I got to change the homework date. I was going to do it last night. I somehow forgot. The chapter 29 homework. I'll make it due. I was going to give you guys 2 more days, so I'll make it due. Today's the 3rd, right? Do you want to make it due Friday or Saturday?
I think either is fine, but if you do that, are you gonna move the worksheet as well? Because there's a worksheet due Friday as well, right?
Yeah, I'll make that do Saturday then, or
Okay.
Sunday. The worksheet doesn't. I mean, the worksheet's not that long. I can add both. I can add 2 days to both. My only concern is that this is due on that day too.
Yeah, that was my concern is if we have the homework, the worksheet, and the quiz on Friday, that's a lot to prepare for, and we have to do the lab.
How's that?
And that works for me.
Okay. Let's do that then. Hopefully that's fair enough. Okay. But I got to remember to go online tonight. I was going to do it last night. Somebody emailed me. I said I was going to do it, and then I never did it. I just got distracted. Sorry. Okay. So I'll fix this. I have a meeting right after class. I'll fix it after my meeting. Okay.
Yeah, I think.
And then I'll fix the
Oh,
other one too, to Sunday.
thank you.
Okay. Sorry about that. But this is still doing the 10th. Okay. So today what I want to do is I want to continue our discussion on chapter 29. I'm going to finish it off and then I'm going to start on chapter 30. So we're going to talk about, I'm going to do one more example. You can see it on the screen. I'm going to talk about the torque on a loop of wire in a magnetic field. And I'm only going to discuss the case where the field is uniform. If it's not uniform, it's not an easy problem. And this will help you to understand the DC motor. So I'm going to demonstrate the DC motor again. This time I have a nice DC motor set up, and I'm going to show you all the different parts of it. It's much bigger than the one I showed you, the student-built ones. Okay. And then I'll briefly talk about the Hall effect, which is an interesting phenomenon, although I usually don't have time to talk too much about it. And then we'll start on the Biot-Savart law, which is chapter 30. I did send you guys an email with a document on, that kind of gives you the relationship between magnetism and relativity. And so take a glance at it. I'm not going to test you on it, but it's just interesting because as you go through the example, it's not a hard example, and you get to see the relationship that the magnetic field is really an electric field in a different reference frame, in a moving frame. Okay, that's really all it is. All right, so we've talked about the force on a wire in a magnetic field. And really, we talked about the case where the field is uniform and when it's not uniform. And if it's not uniform, basically what you have to do is you have to break up your length of wire into small pieces, ds, and you have to integrate over the length of the wire. So you have to write an expression for ds, know your expression for b, take the cross product, and then integrate. And I did an example last time, which hopefully will help you with the worksheet. The worksheet that I gave you, the problem is not really a complicated problem. It's just a problem that gets you to go through the process of setting up the integral. Okay. And sometimes I ask that on an exam, so I might as well have you know how to do that problem. Okay. And it's taken, it's related to a problem I forget if it was our textbook or one we used previously. Okay, it should be fairly straightforward, but if you get stuck on it, just contact me. All right. I want to just show you an example of a wire and a magnetic field, an application of it, and it's the loudspeaker or the speaker in general. So let me make this figure bigger. The speaker, any speaker, basically has its basic components are a speaker cone, which is basically made out of special cardboard, a magnet, a permanent magnet, so the magnetic field due to the permanent magnet is not uniform. and some coil wrapped around, a current carrying coil wrapped around the permanent magnet, as you see in the figure. In this particular case, the current in the wire varies with time, and it varies sinusoidally with time. And so the force on the loop of wire, which is attached to the speaker, varies with time, and that's going to cause the speaker to move back and forth. Basically, the speaker will vibrate. Now, you do have loops of wire in a magnetic field, but the magnetic field is not uniform, and so you will still have a force on the loop of wire. The speaker will vibrate, and that's going to cause the air molecules to vibrate, and that's your ears convert that into a sound. So I'm going to show you an example. Basically, some students of ours had this nice idea of really designing a real simple speaker, okay? Even simpler than what you see in the figure. So I have a paper cup, okay? And in the paper cup, I put a magnet, and then I put one outside the magnet, outside the cup. And I have a coil of wire. Long coils of wire like this are called solenoids. So I have a coil of wire. I attach this to a power supply. The power supply is a signal generator, so the voltage varies with time. And I'm going to turn this on. And I'm going to set the voltage pretty high. You don't hear anything, right? And so what's going to happen is I'm going to put this into the magnetic field produced by the coil. The magnetic field produced by the coil is going to vary with time. And then in the next chapter, we're going to talk about how to calculate the magnetic field due to a coil. Okay. And so the force on the cup is going to vary with time because you're going to have a time-varying magnetic field, and the field due to this permanent magnet is constant. So I'll put it in. Can you hear it?
A little bit, yeah.
Take it out, it's gone. Put it back in. I don't know how many of you folks are taking 215 concurrently, but this cup has a natural frequency of oscillation. If I make it vibrate at the right frequency, let's see. It'll be louder. Can you hear it better? Is it better now?
Yeah.
And if I take it out, you don't hear it at all, right? Because this cup is not vibrating. When I put it back in, it's vibrating because the magnets are vibrating. And so that makes the cup vibrate. It's a real simple speaker you can make. And if you wanted to, you can connect, instead of me connecting this to a power supply, if I could connect it to your outputs of your iPhone and you play music on it, you would hear the music on this thing. It wouldn't be high quality, but you'd hear it. Questions on that? Okay. So let's consider a loop of wire carrying current, in a magnetic field. Okay, let's consider a loop of wire carrying current in a magnetic field. So let me try to draw a picture of that. It's going to be real hard to draw the picture. Well, we'll give it a shot. Okay. And let's say now the picture shows a permanent magnet, but let's pretend the magnetic field's uniform. Okay? A permanent magnet really doesn't produce a uniform field unless you take the two poles of the magnet, bring them real close to each other, and then the field in the middle is kind of uniform. Okay. But in general, two permanent magnets don't produce a uniform field. So I drew that so that you kind of, in the picture, so you get an idea that that coil, that loop of wire is in the magnetic field. So let's say the magnetic field is this way. Okay, goes from north to south. The current is going clockwise. Now, as the current goes through here, of course, there's going to be forces on each segment of this loop. Let's ignore this part. Okay, let's assume these are so close together. Okay, so let's ignore the effect on here. Okay, although there is an effect. All right, the magnetic field is up here. All right, so we'll just assume the magnetic field's in this region. We'll confine it there. We know that the force on a wire is I, L cross B. What can you say about the force on this piece of the loop, this part of the loop? What can you say about it?
It's 0, right? Because L cross with B is 0 because they're parallel.
Yeah, that's right. Oops. That's correct. So the force on this piece is 0, and then you can say the same thing about the one on the bottom, right? The force on this piece is 0 because this cross product is 0. But this cross product is not 0 here, and this cross product is not 0 here. All right, you have a current, you have a magnetic field this way, and a current upward. And if you use the right-hand rule, you point your fingers in the direction of I, curl them towards B, your thumb points into the board. So the force is into the board here, and of course, it'll be out of the board here. And these lengths are the same. So these two forces, the forces on these pieces are equal and opposite. So the sum of the forces is 0. It's kind of like if I had a square plate and I pinned it there, and I applied a force here, and I applied a force here, the sum of the forces is 0, but this thing is still going to turn, right? Those two forces cause a rotation. That's because those two forces exert a torque on the object relative to this pivot point. And so there's a torque on this loop because these forces are going to cause the loop of wire to spin. So how do we calculate the torque? Well, there's a couple of ways. The hard way is the following. Now, in order to do this, I actually have to draw this from the top. I'm going to look from the top of this thing, okay? I'm going to draw this at some angle. If you look from the top, the current here is coming towards us. In here, the current's going back into the board. And this force, let me draw in red. This force points downward. This force points upward. Let me call this angle phi. And this is the center. I want to calculate the torque about the center of this guy. We'll call this the width of it.
I'm sorry, are you able to explain that drawing again?
This one?
I'm not fully following, yeah.
This is looking from the top. Okay, so if you're looking from the top, the current here is coming towards you. That's this one. And if you're looking from the top, this current's going away from you.
Got it. Okay.
Okay.
And then what's the line in between them?
This line,
Yeah, is that just?
that's just
Yeah.
this piece. I just
Okay,
drew it at
fine.
an angle.
Okay.
I drew it at an arbitrary angle because this thing changes, right?
Yeah. All right. That makes
Okay.
sense. Thank you.
All right, so now we want to calculate the torque. The torque, and I'm going to do two different ways. One way is going to be hard to see what the results are. Obviously, the torque is going to point towards us. I'm sorry, no, the torque is going to point into the board. Okay, R cross F. So let's do R cross F. Torque is R cross F. And I'm going to call, this is my R, I'm going to call it W over 2. I'm going to be very general. And this is W over 2 in the opposite direction. These two forces are in the opposite direction. So the torque is due to these forces. These add up but F is I, L cross B. Now writing it in this form is very difficult to interpret what this means. Okay, so this is what you would have to calculate. There are cross product identities you can use and simplify that. I don't want to do that. I don't want to go through that. That's complicated. Let's just focus on calculating the magnitude of the torque. Okay, that's going to make it a little bit easier. So let's do this. Let's calculate the magnitude of the torque. And you notice force times lever arm, right? So the torque is going to be the magnitude of, is going to be this distance times the force, which is basically going to be I times L times B, because L and B are perpendicular to each other in this case, times the sine of phi. That's this is the lever arm. And there's two of these terms. And so this is going to give me W times L times I times B times the sine of phi. And the direction of the torque is into the board. It's perpendicular to both F and W. Well, what's W times L, though? This is W, this is L. What's W times L? What's length times width?
Oh, the area.
Area. So really this is the current times the area times B times sine of phi. This tells you still that though there's a cross product involved. So I want to write this as a cross product. And I'm going to define an area vector. Like we do when we do Gauss's law. And this area vector, the direction of this vector is normal to the surface of the loop. But there's a problem. Hold on a second. There's a problem with the normal to this loop. What's the problem with it? How many normals does that loop have?
Is it 4?
Well, I mean, to the plane of the loop, right? This is the plane of the loop. Isn't there a normal that points towards us and then one that points into the board?
Oh, yeah.
So how do I define this A? Because this is an open surface. Well, if I want to make it consistent with the torque direction of the torque vector, the direction of this A is defined in the following way. Using another right-hand rule. You take your right hand, you curl them in the direction of the current, and your thumb points in the direction of the normal to the loop. Okay? So this area vector is defined by a right-hand rule where you curl your fingers in the direction of the current, your thumb points in the direction of the normal to the loop. And so now we have an expression for torque.
Wait, I'm sorry. I have a question on that.
Sure.
So for the right-hand rule, you did the top current, correct? Right.
Well, just the loop in general. The current's going clockwise, right?
Yeah.
So curl my fingers clockwise, and my thumb points in the direction of the normal.
Okay. Because I was thinking if you do it the bottom one.
Oh, here?
Direction. No, well, the one on the horizontal.
Oh, yeah. You got to consider the whole loop.
Yeah. Okay.
Yeah. You got to consider the whole loop for this one, and that'll give you the normal to the area of the loop. So really, I can write it like this. Where n is the normal to the loop. So, but the thing is, this equation for the torque is really if I have one loop. What if this thing was made up of 50 loops? Then I'd have to multiply this by 50, right? Right? If there was 50 of these loops in the magnetic field, each loop will experience this torque. So really the total should include the number of turns in my loop. So if this was wound around 50 times, I'd have to multiply this by 50. And so this is the expression for the torque on a loop of wire in a magnetic field. And then the magnitude is going to be N, A, I, B, sine of phi, where phi is the angle between the normal to the loop and the magnetic field. Okay. And if you look at that picture, that's what I drew. The yellow dotted line represents the angle between the normal to the loop and the magnetic field. Okay. Now, a lot of times we define this, we don't always write it like this. We define something called mu or m sometimes you'll see our book, it'll be written as mu, but some books it'll be written as m, and we call it, say it's n a or NIAB. I'll write it like this. And this is called the magnetic dipole moment. And of course, this has its origin really at the microscopic level. However, I don't have time really to get into the details of this like I did for the electric dipole moment. This is the analog of the electric dipole moment. Okay, so then we can write the torque as mu cross B. But mu is given by this term. And B is uniform. Let's not deal with, I don't want to talk about non-uniform fields. Or you can write it as M cross B. Some books write it as M cross B. So this is the magnetic dipole moment. Okay, so a lot of times you'll see it this way. But really, this term is really used when you're talking about a microscopic object, like when we did with point charges. Okay. Again, the torque is the units for Newton meters. Okay. If you talk about an electron in an atom going around, the electron going around in an atom, it's producing a current. It has a dipole moment because of its orbital angular momentum. In fact, the electron itself has its own intrinsic magnetic dipole moment because of its spin. And we said the other day that the magnetic properties of material are mainly due to the electron spin. And so in order for, you would need to talk a little bit about the magnetic dipole moment if you wanted to talk about the magnetic properties of matter. And it is discussed in chapter 30, and you should read it on your own, even though we're not going to have time to cover it. But at some point you will cover it if you take physics again, at least E&M, whether it's a physics course or an engineering course. Okay? Now, this magnetic dipole moment, when you put it in the magnetic field, it wants to align itself with the magnetic field. Just like the electric dipole moment wants to align itself with the electric field. Okay. In this particular case, the normal to the loop wants to align itself with the magnetic field. That's what it tries to do. So if you have a loop of wire carrying current and magnetic field, there's going to be a torque on that loop of wire, and that loop of wire is going to want to rotate. So get the idea now. We're moving towards how a motor works. Okay, because a motor is a loop of current carrying wire rotating in a magnetic field. I think I froze, right? Actually, my video camera froze. Oh, it's fine now. You guys can see me okay, right? Or, I'm not frozen, right?
No, you're not frozen.
Okay, my video camera froze for some reason. Okay, so this is I can show you this video because it was from MIT. It's for educational purposes. So let me show you this video. This shows you a loop of wire in a magnetic field. Magnetic field points upwards, and the green arrows show you the forces on the various segments of the wire. So where would you apply this idea? Well, here's one, an ammeter. This is the old-fashioned ammeter, where you had a loop of, basically, you had a loop in a magnet, and when you ran current through it, that loop would rotate. And that spring mechanism was designed so that the loop would rotate based on how much current was going through it. And you just calibrate that thing and you have an ammeter. So what I want to do now is talk about the electric motor, the DC motor, which is your big project you're doing. Well, it counts as a lab, but I see it as a big project.
That's our next lab, right?
I'm sorry?
That's the one that's due in 2.5 weeks, right?
Yeah, that one's due December 3rd. So what I recommend is after you're done with this lab, you can start building it. It really doesn't take long to build. You're just wrapping wires. The hard part is making it work efficiently. Okay. The DC motor converts electrical energy into mechanical energy. It's really a generator working backwards. And I'm going to talk about the generator when we get to chapter 31. And I'm going to use the same device as I'm going to show you today. I'm going to run it as a motor today, but next time I'm going to run it as a generator. All it is a loop of wire turning in a magnetic field. So I'm not going to plug it in yet.
Professor, you froze this time.
I did freeze. I'm okay now, right?
Yeah, you're good. You're good.
Okay. I'm going to get rid of the slide. And I'm going to zoom in. Okay. So this is a like a demonstration motor. Okay, and it has three main parts. And this part that rotates, this is the coil of wire that's in the magnetic field. This is called the armature. And this is what does the work. Okay, so this part is the armature. These loose things that make the electrical connection are called the brushes. And this is called the commutator. Okay, and one thing I want to point out to you is that this commutator is split into two parts. You can see on both sides, it's split into two parts. And there's a reason for that, and I'll get to that in a minute. So this is called a split ring commutator. These are the brushes. Okay, and then this is basically part of an electromagnet. So this goes to a coil of wire. I don't know if you can see it. There's a coil of wire. We're going to run current through this thing. It's going to turn all this into a magnet. And then this becomes a magnet, and we're going to have a current going through here. And basically, we're going to have a loop of wire and a magnetic field. It's going to produce a torque on this thing. It's going to make it spin. So let me connect this to electrical power. I don't know if you can see this. This box is what we're going to have in the lab for you to practice on. This is way better than the batteries you are using. This can supply a lot more current. Okay, that's why it's nice to come to campus and test out your motor. Okay, because this works way better than the batteries you're using to test it out. I can vary the voltage and all that kind of stuff. In fact, the only problem I have with this is I can't minimize the voltage. And so this sucker is going to actually turn pretty fast. A lot faster than I would like. And when I ran it yesterday for my other class, this was drawing like 7 amps. So, so I connected to the power supply. I connected the electromagnet and the armature. But I did it in parallel, so I'm cheating. You guys are going to do it in series. This is why I'm probably drawing a lot of current. I did it in parallel because it works more easily. And I got to plug in my power supply. Sorry, forgot about that. So let me plug in my power supply. And there's friction in this, so I got to give it a little bit of a kick. Why isn't it not working today? Okay. Of course, this, in terms of doing work, it's not the most efficient motor. It's drawing between 7 and 8 amps on my power supply. And I only have 2.8 volts on it. So if this can run on 2.8 volts, your motor should be, which is much heavier than your motor should be able to run below 3 volts. Usually I use a different power supply. It wasn't available, and so it never spins this fast when I do it in class. That thing was going pretty fast. Okay, if I ran the current up, then it would spin faster, but then I don't know if I'd melt the wires, because there was a lot of current going through this thing. So I wanted to say something about that split ring commutator. Why do I have to split the ring? Is that blurry or is that okay?
Looks good.
Okay. So, why do I have to split the ring on this commutator? Well, what happens when this thing flips by 180 degrees? If I flip this by 180 degrees, right, then the current looks like this. The current goes in the opposite direction. When this thing flips by 180 degrees, the current, you see a current going in the opposite direction. What does that mean then to the torque? What happens to the torque if the current goes in the opposite direction? Well, if I flip the current in the opposite direction, that changes this normal to the loop. And so that changes the direction of the torque. So instead of the motor rotating in the same direction, what's going to happen is the armature is going to want to go like this, back and forth. You just go back and forth instead of spinning in one direction. Because of the fact that when this thing rotates by 180, the current switches direction. And so what do? You split the commutator. You split the commutator, like so, and you're going to do that in your motor too, so that when the motor flips by 180 degrees, the positive and negative are swapped, and that keeps the current going in the same direction, and so your torque stays in the same direction all the time. Okay? So your torque stays in the same direction all the time when you do that, when you split it. That's really important for a DC motor. For an AC motor, it's not a problem. In fact, this device that I'm showing you, let me get rid of that slide, can be run as an AC motor or DC motor. If I wanted to run this as an AC motor, all I would have to do is just move these brushes to these commutators. Because AC changes direction automatically, okay? DC doesn't, and so I have to split this ring so that when this thing turns by 180 degrees, in fact, right when you get to this point, you change from the top half, you make this contact changes from the top half to the bottom half. That reverses the direction of the current, and you want it to happen when the torque is 0. The torque is 0 when the armature is in this orientation. Why? Let me rotate this so you can see it better. In this orientation, the torque is 0. That's when you want the current to change directions. Why is the torque 0 in that case? Well, what is the direction of the magnetic field and what is the direction of the normal to the loop? They're parallel to each other.
Yeah.
And so there's no torque. This is when you want it to switch. You don't want it to switch when it's over here, because if it switches when you're over here, you're doing it when the torque is a maximum. You don't want that to happen. Okay? And that's an important consideration when you're building your motor. Because if you don't think about that, your motor won't work at all. Okay? Usually I don't give that hint right away. I had a student one semester who couldn't get his motor to work. He was very frustrated. He did a beautiful job building his motor. And then we figured out his commutator was not oriented properly. And once he oriented properly, it ran at 2 volts. And just little things like that are what are going to affect your results in that lab. Okay? And I'll tell you, if you come to campus and test it out, it makes a huge difference. I mean, the power supply I have here is way better than the battery you're using. Okay. A couple more things then about the motor. Again, the armature is basically the coil of wire mounted on a cylinder. Doesn't have to be a cylinder, but it's the part that does the mechanical work. The commutator and the brushes. The brushes are what allow you to deliver electrical energy to the armature. The commutator has to be split for a DC motor. It doesn't have to for an AC motor. Now, I should say this is called a brush motor, right? There's brushless motors too. But I want you to build a motor with a brush, with the two brushes. Okay? I mean, I was trying to look for all kind of videos on motors. Most of the motors are either that you see online are induction motors, which are AC motors, or just brushless motors. There's not too many videos on motors with brushes. I did for your lab put videos either in the discussion board or in the module of the motor that you guys are building. Some folks, there's like 1 or 2 videos that built a motor that looks just like the one you're building. So you get an idea of what it looks like and when it's done and how it works. So you should watch those videos. But yeah, I would get started on it right after you do the DC circuits lab, because I know that's going to take you some time. Okay. So this figure shows you what happens. This is probably a better figure than what I drew on the board. When the loop rotates by 180 degrees, the current reverses direction, and that reverses the torque, and you don't want that. That's why you have to have the split ring commutator. All right, I want to briefly talk about one more topic in the chapter, and that's the Hall effect. Suppose I have a conductor, a thin conductor in a magnetic field, and this conductor is carrying current. This effect was discovered by Hall. I think it was, let's see, what year it was. 1879. Let me draw a conductor. And is carrying current to the right. If the current's to the right, the electrons are drifting to the left. Okay? The electrons are drifting to the left. Let's have a magnetic field that points into the board. Now this effect is very small, so you have to do this with a thin conductor. Meaning, you want this area to be big. Okay, you want A to be big and L to be small. You want rho L over A, the resistance to be small. If you use the right-hand rule on these electrons, with this field going into the board, this is not a good picture. Hold on a second. It's too steep an angle. It's probably still not good, but that's okay. If you use the right-hand rule, you'll find that the forces on the electrons are upward. And what that means is this field is going to force the electrons to move all the way to the top of this conductor. If the electrons move to the top of the conductor, then you're going to have a deficiency of electrons down here. So in the end, you're going to have positive charge here, negative charge here. You're actually separating charge in this conductor. and you have an electric field that points upwards. And this happens until the force due to the electric field equals the force due to the magnetic field. And so this electric field is induced because of the fact that it's in the magnetic field is just the drift velocity of the electrons times B. But B is uniform, so that means E has to be uniform. So if I have a uniform electric field, I know that when I have a uniform electric field, I can easily write the electric field as the potential difference divided by D. And so I'm going to have a potential difference between these 2 points. This is going to be a lower potential. This will be at a higher potential because the electric field points in the direction of decreasing potential. So lower potential, higher potential. And so this voltage I can measure. It's called a Hall voltage. And so the Hall voltage is just the drift velocity times the magnetic field times this distance d. And that's the Hall effect. And this is a small voltage. You do need a very sensitive multimeter, a voltmeter to measure that. Some conductors, when you put some conductors, I think it's indium, in a magnetic field, this Hall voltage is greater. The size of the Hall voltage depends on the material you're using. And I think indium works the best for this particular case. And this is the Hall effect. And it has important applications. For example, you can use the Hall effect to measure magnetic fields. If you know the properties of this thing, if you know the properties of this material, the Hall voltage is going to be proportional to the magnetic field. So if you know this, you know that. You can calibrate it to measure a magnetic field. And so a lot of devices that are used to measure magnetic fields are called Hall probes. The Hall effect is what was used to determine whether it was electrons or a positive charge moving in a wire. If you write the expression down for current, you can also you can actually measure the number of charge carriers per unit volume in your conductor. You can also measure the drift velocity. And again, you can also use this to measure magnetic fields. So it's kind of an important thing. We usually cover this briefly. And then there's also something called the quantum Hall effect and the fractional quantum Hall effect. And I put a video in a module on this, so you can take a look at it. And there's a person who discusses the various Hall effects. Okay. You should just understand conceptually what's going on here. So you should understand this picture. And there's a homework problem basically that gets you to tries to kind of get you to understand what's going on conceptually in the Hall effect. Questions on this? Okay. So chapter 29 just basically introduces us to the basics of magnetic fields, some of the applications and effects. Oops, I didn't see the chat. Hold on a second. Oh, what was the lowest amount of volts someone ran the motor? I think it was 0.8. 0.8, around 0.8 volts. Tyler can tell you what that is. We used to allow the motor to run in parallel, and so that I had when I ran at 0.4 volts in parallel. But I want your motors to be in series. Okay. Just a second, I'm tripping over cables in here. All right. So now what I want to do is talk about sources of magnetic fields. How do you calculate them? And between now and Friday, too, I'm going to spend a little bit of time on Friday discussing sources of magnetic fields. Now, there's two sources, right? There's current-carrying wires. There's current-carrying wires. And then there's the magnetic materials. I'm not going to have time to really get into the properties of magnetic materials, so I'm hoping you'll read that on your own. I'm going to focus on basically calculating the magnetic field due to current-carrying wires, and I'm going to show you two different techniques over the next couple of days and discuss a couple of applications. So the first one I want to look at is the Biot-Savart law. I'm going to use today and Friday to discuss this. Okay? And I'm going to end a little bit early today because I actually have to run to another meeting afterwards. So I'll use some of the time on Friday to discuss some of this. Years ago, Ørsted showed, and I'm going to bring it in on Monday, or maybe I might bring it in on Friday. Ørsted showed that a current-carrying wire will produce a magnetic field. If you put a compass near a current-carrying wire, the compass will deflect. Okay? And the direction of the current is easy to determine. The direction of the current is given by the right-hand rule. Another right-hand rule number 3 or 4. If I is this way, you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. Okay? Point your thumb in the direction of I, your finger curl in the direction of the magnetic field. Look at that figure. Okay. And so Biot and Savart looked at, or they conducted experiments to study the magnetic field due to an infinitesimal wire carrying current I. They also had an expression for the magnetic field due to a charge. If you have a charge, Q, moving, let's say, in this direction, and you wanted to find the magnetic field due to this charge at this point, that's my r hat, the length of the vector. You can show that B is a constant and is given by that expression. Okay? All right. Okay, I think I'm going to have to end the class early today because I think some things come up. I need to run. You guys okay with that? I'll discuss this more on Friday.
Thank you, Professor.
Okay, sorry, I need to run it quite a little bit early.
Thank you. Are you on? Sorry, may I ask a quick question?
Yeah, go ahead.
Are you on campus at all tomorrow?
Not tomorrow. I'm here today until 1.
Okay.
Okay?
Yeah, thank you.
All right.
All right.